Hello everyone, welcome to this presentation. My name is Sofiane Lounici. I'm a PhD student working at Cybersecurity Research, and I'm going to present you the paper Yes We Can, Watermarking Machine Learning Models Beyond Classification. This is a joint work with Mohamed Njeh, Orhan, Ermis, and Melek Önen from Eurecom, and with Trabelsi from Cybersecurity Research. To begin with, I will explain the motivation of this work. With the advent of the big data technologies, companies are looking to leverage machine learning models to improve their businesses. However, since the cost of a machine learning project represents in average between $50,000 and $150,000, it is often a strong investment for companies. In particular, the training cost of state-of-the-art models, such as the GPT-3 model developed by OpenAI, has been evaluated to $12 million. Due to the important investments, machine learning models need to be considered as assets, offering a competitive advantage to the model owner. Thus, they became a privileged target for thieves to bypass the machine learning development costs and to acquire a stolen version for their own benefits. A solution to protect the intellectual property of the models is called digital watermarking. Watermarking is the process of embedding a hidden, unique, and non-destructive modification into a model through data poisoning. Indeed, the original model is overfitted to a set of particularly crafted instances called triggers only known by the model owner. The detection of this modification, based on the behavior of the model on the triggers, constitutes a proof of ownership. In the past few years, several techniques have been developed to create robust and efficient methods to embed and verify watermark for image classification. However, an important part of machine learning tasks currently used in production is not image classification. A majority of tasks considered are regression, text processing, or reinforcement learning tasks. Such models show major differences with classification models and therefore may not be compatible with existing watermarking solutions, especially regarding the trigger generation. In this paper, we propose to study watermarking solution beyond image classification tasks. We consider machine translation, translating from a source language to a target language, a reinforcement learning task called the inverted pendulum, where the model needs to balance the pendulum with left or right movement, and a regression task where the goal is to predict the revenue in dollar per customer of a Google merchandise store. We present different metrics to verify the presence of the watermark in the model beyond accuracy. We also propose different trigger generation techniques for each of the tasks and evaluate the robustness of the watermarks for these models. To evaluate the performance of the models, we define performance metrics for the tasks. Beside the accuracy, we have four other metrics. For the translation task, we have the rouge and bleu score to measure the quality of the translation. For the regression task, we consider the mean absolute percentage error, MAPE, and the root mean square error, RMSE. To verify the presence of the watermark, we compare the chosen metric sigma to an ownership threshold beta with a particular case of the regression task. For non-regression tasks, we define beta with respect to the size of the trigger set, the number of labels n, and the confidence level in the verification process epsilon. For the regression task, we define beta for RMSE and MAPE with respect to a quantification parameter Q. For the definition of the models, we consider three main techniques for the trigger generation. First, we consider the external watermark noise technique, where the input is random data. For instance, random data in the case of text data is a random string. The main advantage of this technique is its simplicity because it's easy to generate. However, this kind of trigger input is easy to detect by an attacker. The second technique is called external watermark selected, where the trigger input is non-random data but not belonging to the original training data. For instance, in a French to English translation, a Spanish word is chosen as input. Finally, we have the internal watermark, where the trigger inputs are solely composed of modified original data. For image classification, the trigger input could be an original image modified with a precise patch in the top left corner. For translation, a rearrangement of words in the source language to obtain a complete different translation. Overall, the three techniques can be applied to the different tasks with different objectives. We consider two types of attacks on the models. On the one hand, removal attacks, where the goal is to modify the watermark model with retraining or pruning, attempting to remove the watermark. On the other hand, evasion attacks, where the attacker is implementing an input filtering module between the stolen model and the API access to filter potential trigger instances. The evasion attack can be split into three categories, from the easiest to implement to the hardest. First, the heuristic attack intends to detect through a set of rules if the input data is potentially a trigger instance. Then, the compression attack, which aims to pass the input data through an autoencoder in order to remove potential trigger information before submitting to the model's outputs. Finally, the voting attack, whose goal is to submit the input to the vote of several watermark classifiers. We evaluate the three evasion attacks with the removal attack on the four tasks and on the three trigger generation techniques. In the experiments, we evaluate the fidelity of the watermarking techniques. We expect high fidelity, meaning high performance on the trigger set without damaging the performance on the legitimate set. We define a common measure, called ratio, between a given metric with or without watermark. High ratio implies high fidelity. Next, we evaluate the robustness of the watermark model to the two types of attacks previously mentioned. We use the same ratio to investigate the performance metric before and after the attack. We led a comparative study for the four tasks and on the three trigger generation techniques, plus the legitimate data, based on the defined metrics. By analyzing the impact on the triggers, we measure the fidelity. We notice that watermark models do not perform significantly less than the clean models for all tasks on the legitimate data. Hence, we have a high fidelity in all the situations. We observe the performance on the trigger set and we compare the obtained metrics to the predefined thresholds. In all of the situations, the verification is successful for the watermark model. In the second part of the experiments, we evaluate the success of the attacks against the watermarks. The efficiency of the attacks depends on the type of attacks considered. We run attacks on the watermark models for the task, and we underline in red the case where the attack was successful. In blue, in the case where the metric was close to the verification threshold. First, we observe that the adversary is successful in a significant number of attacks. However, most of the successful attacks are amongst the hardest to implement. We observe that different tasks have different responses to a particular type of attack and to a particular type of trigger generation. Moreover, we observe for a given model, task, attack, and trigger generation that the simple choice of metric could have an impact on the ownership verification. In the case of the regression task, choosing RMSE or MAPE could lead to a valid or non-valid verification. The interpretation is that some metrics are more sensitive to prediction outliers, hence more sensitive whether or not a trigger was correctly predicted. Thus, RMSE metric is more adapted for watermark verification than MAPE due to their respective behavior on prediction outliers. Overall, an interesting idea for watermark verification could be to choose different metrics to assess the performance on the legitimate and on the trigger data. In conclusion, we presented a study of watermarking solutions applied to different machine learning techniques, showing that it is possible to propose a watermarking process for non-classification models and for data sources beyond images. We displayed several attacks against different types of models and offer a discussion on the choice of metric to verify a watermark. Future work may consist in developing more complex removal attacks and extending current work to include more models, such as autoencoders or clustering methods. Thank you for attending the presentation, and I'm ready to answer your questions.